All right, well, there's a loaded question. Why don't some students learn maths even when we teach it well? And obviously there's an absolute multitude of reasons why this is the case. I simply want to look and talk about one factor that affects our ability or inability to do maths, and it's actually really the same thing that Chris was pointing to in his last talk. This idea, are we teaching them procedures or are we teaching them to think? And they're sort of different things. And I've gone purely as a literature review, so I've tried to look at the evidence base out there, what actually works, as opposed to the multitude of theories that are out there, things like neuroplasticities. It's a real buzzword, this idea of changing people's way of thinking, and there's a multitude of people publishing opinions. So I've tried to stick to the published literature that actually demonstrates something, so we kind of know where we're at. And what I'm looking at is how we construct mental models when we're learning maths, how we encode maths in our brains. So Margaret Peyton's a writer, and in a piece she wrote about how it's socially acceptable in Australia to hate maths and to say you can't do it, she wrote that it seems like the groundswell of people who hate, fear, or are frustrated by maths are in the majority. So I guess that puts us in the minority. And it also makes us different from many of our students, especially students like Charles's students who are there under duress. So the way we, and one of the things that makes us different is the way that we encode maths when we're learning it compared to these other students. So to start off with, I want to start where this research started, which was in reading. So think of a book you've read. You're probably going to sleep after an hour of sitting still. So if you've read a good book recently, pop it in the chat. Let's see what comes up. Okay, no one's read anything. No one wants to talk to me, everyone's already asleep. Well, I've just finished reading a book about the Australian code, cracking the naval codes during World War I. And it was really good. And my poor husband got a blow-by-blow account of everything that happened in it this morning. The thing is, when we read a book, we're reading hundreds of words or thousands of words, and yet effortlessly we can recall sort of a blow-by-blow sequence of everything that happens in the book. But there's no way we can recount those words in that sort of order. So what's going on? You know, how is it that we can read a book, a good book, and effortlessly know and recall and understand everything that's going on? This is interesting, because if we could do this in maths, wouldn't it be cool? That is not where I'm going. So in 1971, a psychologist called Alan Pavio put forward a theory that he called dual coding theory. And what he postulated was that both visual and verbal channels are used to represent and store information. For example, if you hear the word dog, you both hear the word and you form a mental picture of what a dog is. Our mental pictures of dogs are probably different, but we're using both verbal and visual channels at the same time. That was his basic postulate. And the idea was that then when you read the words in a book, it goes into the left side of your brain where it's processed linguistically, but at the same time, the right side of your brain is putting forward a series of images or a video of what's going on and all the information stored in that video. And that's how you can store so much content so easily. It's chunked into that one visual image. When we fast forward to the present, this is regarded as a gross simplification of what's actually going on. And most theoreticians now agree that it's more complex than this, and we don't have sort of a visual channel and verbal channel, but in fact the information's distributed in lots of different places across our brain. There's some verbal, some visual, some emotional, some tactile, you know, all different places, some abstract and so on. And all of this put together, that's what we're talking about when we talk about a mental model. The information can be stored here or there in the brain, but when we put it together, we get this model of what's going on. And it seems that we do exactly the same sort of thing when we're doing maths as we do when we're reading. We're building mental models. And a quick example, if you hear the word integers, Right? A whole lot of ideas are going to pop into your brain. Here's a few that popped into my brain. And I'm sure, you know, you've got others as well. But these things put together, they sort of form your idea of what the integers are. And see, when we learn maths, we who don't hate maths and can do it, we either consciously or unconsciously form some sort of a mental model that lets us synthesize the new information and understand it in the context of what we already know in a way that's consistent and makes sense. And these models develop over time, going from concrete through to abstract. Now, for most people, with reading, this happens automatically. In general, when we're teaching kids to read, we teach them their phonetics, we give them simple books with pictures, and they automatically pick up this mapping, this idea that you can get a greater understanding or a model from the words. In maths, it appears that this does not just happen for most people. It's not something that happens automatically. It happens for a small minority of people who tend to be us and physicists and so on. But for the vast majority of people, it's not something that just happens by itself. Interesting, huh? So the thing is that in terms of your ability to do maths, how well you can conceptualize something obviously affects how you can solve it. For example, if the only model I've got of integers is a one-to-one correspondence between integers and rumbletimes, I'm going to be a lot more limited in what I can do with integers than you who are experts and have all these other models, like the idea it's a ring, it's a subset of R, and so on and so on. So the quality of mental models affects your ability to do maths. Before I get on, let's do this. All right, so the state of play in terms of maths education is essentially that most students never develop mental models for maths at all. Talk more about that in a sec. But of those who do, the majority develop mental models that are either not good enough, contain contradictions, are just plain wrong, or are useless. That's a pretty sad state of affairs. I want to do a short experiment before we go on, just to help you to stay awake, if nothing else. So make $1.70. It's too easy, right? It's a super easy problem. I don't care how you do it. You've got an infinite supply of 50 cents, 20 cents, and 10 cents, and you want to make $1.70. Really easy, right? But it's easy because you understand how money works. You've got mental models that tell you how money works. You've got mental models for how to do addition. You've got mental models for place value. You've got mental models for a number line that let you compare the size of numbers and see if you're getting close. Okay, now try this one. Don's laughing at me. I want to say, when you get it, stick something in the chat, but then I'm scared I might go overtime if I have to wait. So the thing is, suddenly it's got a whole lot harder, hasn't it? And if you're doing it, you're either probably frantically trying to come up with an underlying pattern that lets you solve it in general. As mathematicians, that's probably what you might be doing. Or you might be, or Joshua says 20 times I can keep the change. I have to pay that. Or you might just be doing trial and error and bashing it till you get somewhere. Or you could just be waiting for someone else to solve it, and then you'll learn what the answer is from them. Okay. The thing is, if you do it in either of those two ways, as soon as I change the problem, you've got to learn a whole new case all over again, because you've carefully learnt that I make $1.58 by this combination, but you're none the wiser. You don't have any sort of model to back you up. And this is what doing maths is like for a lot of our students. It is prohibitively difficult because they don't have the right pictures in their heads. All right, enough simulation. So what does life look like in the brain of a maths student? Now, in these 6 characteristics, it's very bipolar. Experts are like this, students are like this. Obviously, this isn't the case. There's a continuum, et cetera, et cetera. But the first first characteristics is some, or according to Greco and Merryn, most students don't have mental models and rely on memorised procedures. This is the worst case. A lot of these students don't even realise that there's more to maths than just memorising a bunch of random formulas or following algorithms. They don't realise that maths is actually a cohesive whole and that they should have a mental model that joins these different formulas and concepts together and explains things. They don't even get that this is what maths is about. And so they don't look for them. When you teach something to this type of student, out of everything that you say, they look for a procedure or formula to store because that's how their mental setup is working. They don't store the underlying or the big picture or the process because there's no place for these in their mental framework. So you can explain to the cows come home, but they've got no framework to store it in and they take nothing of that away except what's the formula. And, these students get through exams by using procedures, and part of their procedure will be to use cues in the questions to know what to do. They'll just latch onto trigger words or variables and know which procedure to pull up. Here's an example of this. This comes from Don's course in preliminary maths for engineers. I had access to some absolutely gorgeous answers. This was a differentiation quiz. They're asked to find the limit. Here's a student answer. Use the quotient rule. And you can see that this student has used a procedure which says, if I'm doing differentiation and I see a fraction, I use the quotient rule. Now, we could go in and say to this student, no, that's not what you do. This is a limit. And because it's a limit, we need to do this. But all you're doing is replacing one procedure with another procedure. Student has no more understanding. They just have a correct procedure. And that's where it's at. Okay, secondly, novices choose what to do based on surface features of a problem. Experts choose models based on the structural features of a problem. In translation, novices will see a problem as a set of details, whereas experts see it as an overarching cohesive whole. But another example from Don's course. Don, you're famous. Here we've got a picture of the Golden Gate Bridge. Let me see. Yep, okay. Now, there's a lot of words there, but what they come down to is that we've got two towers on the bridge. Both of the towers are sitting at a height of 155 metres. So as competent mathematicians, what we can see is we're given the equation for the arch and we're going to shove in y equals 155 the height and solve it, and it becomes a very simple problem and all falls out. Very few students did this. Can you guess what the students did? You probably can, right? The student said, there's a quadratic there. I'm going to shove it in the quadratic formula, and came up with rubbish. And the majority of students did that. You can see they're working off surface features. They can't see it as a whole. They jump in, find a detail that looks relevant and solve based on that detail. Okay, going on. Experts and novices have different levels of detail in their models. This is only an illustration. It's not a true picture of a mental model. I'm going to quote Bjorklund to you, who says that strong students make more detailed mental models. Expert mental representations demonstrate superior extent, depth, and level of detail. They accommodate more interconnections and are more geared towards action. Weak students, on the other hand, have simpler, fuzzier models with less interconnections that are less useful. And it's also been postulated that this is a bit of a cyclic thing because weak students can't ask good questions because their model is so vague, they don't got no space to fill in the details. Whereas a good student has a good model, and so they can ask more precise questions to fill in the model better. And so you get this cyclic effect, the spiral effect, where good students get better and bad students get worse. All right, next is that students comfortably hold contradictory models and experts don't. And it's been, Greco and Moira say that this is because students' models are purely functional. The way we teach them, they just have to have a model to get them to the right answer. They never have to address any contradictions or inconsistencies inside their models. This example comes from Davis way back in 1983, but it illustrates so beautifully. He was talking to school children and he wrote down 2/7 plus 1/7 and asked them for their answer. Typically, they gave him 3/14. Then he took them over to some Cuisenaire rods and they built it. And typically they got an answer of 3/7. So then he took the children one by one and he said to them, well, we did it this way and we got this. We did it this way and we got this. What's the go? Are they both right? And he got one of four answers in roughly equal amounts. Either the symbols are right, the rods are wrong, or the symbols are wrong, the rods are right, or a distressed looking child who says, I don't know, please tell me what to think. Or, yes, they are both right. In symbols, this is the correct answer. In rods, this is the correct answer. And these students comfortably held this contradiction. Number 5 is very similar, and so we're using the same example. When given new information, strong students adapt their model to integrate the new information. So the strong students here were convinced by the Cuisenaire rods and decided that the way they'd done it in symbols must have been wrong. They changed their model. Whereas the weak students either just added it to their model, well, 2/7 plus 1/7 is 3/14 and 3/7, no problem. Or they learnt it as a situational scenario. When I'm working in symbols, I have to get this answer. But when I'm working with rods, I have to get this answer. Again, another contradiction, but this one is contextualised. Depressing, isn't it? Okay, and number 6 is that experts hold multiple models and select the best model for a problem while novices don't. And that's back to my example of integers and me only representing integers as one-to-one corresponds with Rumbletown, whereas yours experts have multiple models and can pick a more sensible model for what you're trying to do. I have the most wonderful demonstration of this. Do you think there's any way we can do a show and tell? Or is this not going to work? Too hard? It's too hard. The technology is just not here. We can have a local volunteer, but what I'll do, I want to try this for yourself, okay? Because this is really cool. So imagine we've got a wireframe cube resting on a tabletop. So you've just got a cube sitting on a tabletop in front of you, okay? Yeah, okay. And the front face is directly in front of you. And there's a perpendicular diagonal going from the front left to the top right. Okay, so far? Yeah, okay. Now, what we're going to do is we're going to take our cube and we're going to grab the perpendicular so it's upright. So the cube's now standing on its diagonal. Okay, so the diagonal is going from here to here. So put your hand on the top corner and the bottom of the cube standing on your desk, okay? Okay, try. All right, now with your free hand, point out where the remaining corners of the cube are. Where are the remaining corners of the cube? Okay, now this is... Okay, so I'm seeing a mix in this room, which is interesting. Geoffrey Hinton did this experiment on over 20 people who worked in vision, and only one of them got it right. N-1 of the people had a vertex on the bottom, a vertex on the top, and they identified 4 more vertices, forgetting that a cube has more than 6 vertices. It seems like this is too hard a problem to do. It's too hard to mental image a cube tipping on its side and remember all the vertices. The one person who got it right in his study moved the axes as well as the cube, and then it becomes a really easy problem to do. Okay, so having the right model can make a problem turn from nearly impossible to possible. It seems like that level of visualization is beyond, is beyond the average person, but if you change models, it's easy. What am I doing for time? Am I running out of time? Probably. Okay, so the summary so far is that experts have good mental models, students don't. We want students to develop good mental models, but most of them don't. Okay, so in terms of teaching and learning, what are the considerations here? So essentially, if we don't teach students how to make right mental models, they'll either memorise unconnected lists of formulae, that's the most likely outcome. They'll attempt to interpret it in accordance to what they know and get some sort of contradictory hybrid model going. Or if you're really lucky, they'll construct a mental model that's actually consistent with the information that they get. And that's what we see. The first one's likely, the B is maybe, and C is fairly unlikely. Rightio. So there's a case for teaching students how to store maths in their brains as well as teaching them what to store in their brains. How do we do this? Well, obviously teaching with conceptual models, that is pictures, it's obviously the way to go. It makes sense. If we want pictures in the brain, pictures in front of them. It's obviously the way to go, and for many reasons, so many reasons, except that it doesn't actually work. If it did work, everyone who taught well would have a class full of students with good mental models who understood. It doesn't work in terms of developing mental models. And I found two reasons for this. One is Groker and Moira's claim that students don't know that conceptual models are conceptual models. They just don't appreciate that what they're seeing is the way they should be understanding a concept as a whole. And they suggest that we should simply tell them. And the other reason is that, well, I've got a couple of quotes here. So let me express it through these quotes. When we teach, it's common to assume that students have acquired or constructed mental models that are copies of the conceptual models and that they can use them. And it's not necessarily true. Regardless of the effort that teachers invest on their task, students limit themselves by learning by heart long lists of formulae and definitions which they do not understand because the phenomena described there are not being interpreted according to the mental models the students should be constructing. So why is this? Why is it that we think students should be learning this stuff the right way and they're not? Well, it seems reasonable there should be a simple and direct relation between a conceptual model in a nice diagram and a mental model, but it doesn't seem to be the case. And what's interesting is it's not only students for whom it's not the case, it's also the case for everyone. Research with active physicists has found that their mental models don't match up with the conceptual textbook models either. But when these same scientists present their findings, they do present them via conceptual diagrams and equations, just like in a textbook. But they never disclose the process that they used to get there. And so students never see the internal mental models of scientists. They never see how to construct them. They're just somehow meant to acquire this skill implicitly. Okay, so we present them with these diagrams, but they're not where we started or how we got there. And it's something that these guys claim is just not being demonstrated. The one place where I thought in maths we do this is often when we're teaching epsilon delta proofs. There's something students find really hard. And it's a lot more common to say, well, you know, here's how I think it through, here's how I choose delta, and now I'm going to write it up backwards like this. So we actually go through and demonstrate it there. But their claim is that in general, we don't do that. When I was thinking about this, it was interesting because my high school teachers actually did do this, but I understand that this is perhaps not common. Okay, so what does work? Right, here's what we do know. We know that nearly all students have access to good processing capabilities when they're dealing with concrete materials. Students can do things when they've got something physical in front of them. Students don't make connections between concrete and symbols, and concrete can be physical manipulatives or digital manipulatives, it doesn't matter. They're very poor at making the links between manipulatives and symbols. We know that good mental representations are very difficult for students to construct, and we know that this isn't given the recognition that it perhaps should have. So this is a claim that we should be explicitly teaching students how to construct good mental models and doing it via modelling. Exactly what that means is kind of open, really. Okay, also, and this is where we get particularly into tertiary. Students don't arrive as blank slates. They hit our classes with pre-existing mental models and procedures for doing things. We all know that. Okay, now if their model is right and it's a working model, it's really easy to adapt it and extend it slightly to take in new information, like extending the number line to the number plane. It's fairly straightforward, it's a small step, and it's achievable. However, if their model is wrong, it's nearly impossible to fix it, regardless of whether the student actually wants to or not. And Rosnick and Clement did a really elegant demonstration of that, which you might be interested in. Okay, and this is why our errors in basic algebra are just so persistent and misconceptions are so hard to fix. Okay, so in terms of fixing misconceptions, because they come in with these wrong ideas, what can we do? All right, doing lots of example problems doesn't work. If you've got a wrong idea, you can do a million example problems and it has no effect on your mental model. Telling someone something doesn't work to change their deep ideas. And you know this from, having debates about people, about politics or religion or climate change, or just arguing with presenting good arguments at someone doesn't change their deep set ideas. And the same is true with mental models in maths. And in fact, Clement says that these sort of approaches are something that can lead to maths anxiety, because if someone has a mental model, they believe they're right. And if their mental model means that they do 1,000 problems and get them all wrong, or their teacher is always telling them they're wrong, then they start to doubt their general ability in mathematical reasoning, and they get stressed out and end up as someone who hates, fears, and is frustrated by maths. It appears that really the only thing that works to correct a misconception or a wrong model is to get the person to use their own model. So not do it for them, but to get them to use their model to predict something. That doesn't work. One that I keep running into is people who want to say the square root of 3 plus 4 is the same as the square root of 3 plus the square root of 4. And, that's something where you can get them to do it, and then show them that you've got Pythagoras' triangle and so on and so on. But the idea is to get them to use their prediction and show that it doesn't work using the rather delightful term recalcitrant data, and then offer them a new model that is both intelligible, plausible, and that actually works. And that seems to be the only way to get a person to change their beliefs there. All right, so how? This is an important point, which I quote McGonagall on. It's quite easy to find suggestions about how to incorporate all these strategies into maths teaching. There's a pack of commercial things out there and opinions and stuff. Unfortunately, research on the effectiveness of these strategies is sparse. And there's a general lack of information about effective intervention. In other words, a lot of what's written out there is it's not necessarily unfounded, but there's no evidence to suggest that it does anything. So there is a growing body of research in college science, particularly physics. There is a good body of research into mathematical modelling in young children. From our point of view, in tertiary maths, we can learn from these. There's obvious differences. Obviously, teaching adults and teaching 5-year-olds is not the same thing. And obviously, teaching a physics lab is not the same as teaching a maths class. We've got different issues, but we can learn something from what they've done. So here's a few techniques that are coming out from these. Actually, telling the students point blank, this is a conceptual model. This is what the picture in your brain should look like. Explicitly modelling the process of developing a mental model for your students in front of your students, using analogies to tap into existing and correct mental models. And this tied in with this is the idea of using storytelling as well as a way of analogy in teaching maths. Actively and purposefully employing imaginative skills can enhance mental modelling skills. I don't think that, as far as I know, that hasn't been explored in tertiary maths at all, but it has been successfully used in some other fields. And here's another one, diagnosing misconceptions in tutorials and labs of an individual approach, and then using the Posner type approach to correct them. So Why do we want to do all this? Well, these sort of approaches have been proven successful in other fields. I'm not suggesting that we go out and copy what they've done because they're different fields, but asking questions about what's going on in the person's head and finding ways to change that has been very successful in some other fields. And also in tertiary physics, there's some really solid work coming out where people are affecting genuine change and improvement in their learning outcomes, looking at mental modelling. And researchers are starting to put this together and come up with recommendations for what teachers should do. It's in early days. So the point of all of this is that I think it's worth thinking about how students store maths in their brains and whether we can teach them to store the maths in a better way that actually lets them use the content in a better way. Right, heaps of references. If you're interested, just ask me. And I've no doubt completely wrecked Chris's time catch up, but that's it. I